Hello everyone, I'm Jun and I'm going to present our recent work about safety critical model predictive control with discrete time control barrier functions. Here is the simulation of a car racing example using our method. So we firstly do a quick recap over other CBF and MPC method on a few slides. So here is a discrete time system dynamics. The control barrier functions are usually defined with the edge functions. So based on this definition of edge, we could define a safe set corresponding to it. Then the discrete time control barrier function are as follow. So we here have the gamma is between 0 and 1, which enforces the edge is always positive with set invariance along the trajectory. We can see that when the gamma is smaller, the constraint is more conservative. Based on the CBF constraints, so there is a previous work proposed an optimal control method, which is called DCLF and DCBF, where the optimization problem is defined as follow. And here we have the CLF constraint, CBF constraint, and admissible control input constraints. So here the CLF constraint represent the control Lyapunov function, which allows us to stabilize the system while enforcing the safety constraint at the same time. So the drawback of the DCLF and DCBF is that we might don't have a good performance since there's no prediction in the optimizations. So when we talk about the prediction, MPC came into our mind. So here is a formulation that people usually do in MPC with obstacle avoidance. Here we firstly have a discrete time system dynamics as constraint, and then the state input constraint, initial condition, and finally distance constraint. We call this method as MPC-DC in this paper because people usually use a distance function as the function g to formulate the distance constraints. So as been discussed previously by other MPC work, the obstacle avoidance constraint will only occur when the robot is close to the obstacle. The intuition behind this is that when the robot is far away from the obstacles, all the reachable states along the trajectory will satisfy the distance constraint. In that case, the distance constraint will be inactivated in the optimizations. So in our work, we would like to unify the MPC with CBF. This allows us to activate the obstacle avoidance constraint, even the robot is far away from the obstacles. So here we change the distance constraint to the CBF constraints. So the changes are very little, but we will see that the enhancements of the performance is very remarkable, and we will see them on the later slides. The first advantage of the MPC-CBF is that this formulation could confine the system movement for the obstacle avoidance with a good choice of gamma. So based on this property, using MPC-CBF can achieve similar obstacle avoidance performance as traditional MPC-DC, while only use less horizon. And because our robot will begin to avoid the obstacle even far away from it. Additionally, we also have some connection between other methods that we have seen in previous slides. So actually, when the gamma becomes close to 1, the MPC-CBF becomes the same as MPC-DC with one step offset. And when the n equals to 1, our MPC-CBF becomes as a soft form of DCLF and DCBF. We actually did a formal analysis about all these properties, and please feel free to check our mathematics and proof on our paper. So we actually will jump all the mathematical proofs, and right now we directly go to the numerical example to see this property. Here we use a 2D double integrator to avoid a circular shaped obstacle to show the properties of our methodology. On these slides, we firstly compare the performance between the DCLF, DCBF, and the MPC-CBF when the horizon equals to 1. So in the figure 1 and figure 2, we can see that the MPC-CBF actually is a relaxing form of DCLF and DCBF when the n equals to 1, and we can see that they almost share the same performance. And when we compare figure 1 and figure 3, we can see that the MPC-CBF did bring prediction into DCLF and DCBF, make the whole trajectory much smoother. To sum up, the MPC-CBF formulation actually operates as a soft form of DCLF and DCBF, while with prediction along the horizon. We are also interested in the influence of different hyperparameters. So firstly, we can see that by using different gamma values, we actually have different performance. On the left side, we can see that when using the lower gamma, we would expect the safety constraint activation much earlier, which means that the system obstacle avoidance performance is much more conservative. On the right-hand side, that we can see the MPC-CBF could actually achieve similar obstacle avoidance performance with less horizon by tuning the parameter gamma. We also actually verify our methodology using a more complicated example when one ego racing car is required to do the car racing competition with other vehicles in a closed racing track. The system is defined on the curvilinear coordinates, and our MPC formulation allows us to track a target speed while keeping close to the center line of the track. So we actually define the control barrier function using a quadratic distance function, and we can see that our method could enable the ego car to overtake other vehicles on the track while tracking a desired speed. Thank you so much for your attention, and feel free to contact me if you have any question, and also feel free to visit our GitHub repo link directly.